안녕하세요. Actually, I don't know Korean, so I just do the presentation in English. So good evening, everyone, and it's my pleasure to be here. It's also one of the first meetups that Celer Network did in Korea. And my name is Qingkai, and you can also call me Victor. And I'm the co-founder of Celer Network. So just a brief self-introduction. Before Celer, I got my Ph.D. from MIT. And I previously also worked at Google and also Bell Labs, working on basically the distributed system and also network security. Okay. So today I'm going to talk about Celer Network's technology stack and also its crypto economics design for layer 2 scalability. And before we get started, I just want to mention that a few weeks. Okay. So before we get started, I just want to mention that a few weeks ago, we just released our alpha version of mobile applications, which is basically contains two applications that is running on top of Celer's option scaling platform. One is instant option payment of a cryptocurrency. The other is option player-to-player gomgo game. So basically, you can find anyone in this world and stake some Hassan Ether and play with them. Okay. So if you have an Android phone, you can scan this QR code and try it right now. Okay. And so far, we haven't do any market push for this kind of mobile applications, and so far it got over 1,000 downloads. And there's over 60,000 payments have been sent on top of Celer's platform. And in total, there are 25,000 gomgo games playing on top of Celer. And these games actually involves around 400,000 option transactions. If we move all of these kind of transactions to the blockchain, it will take 65 days without Celer. So that way you can see how the option scaling can help us to build a smooth user experience of decentralized applications. And we also have a good user retention. Basically, the 7-day user retention is around 15%. So a lot of users are actually very addicted, even though it's a very simple and I would say safe game. And besides the mobile applications, we also release our mobile SDK on the Android and iOS. So basically, you can start to build today. And we just released this Celer's SDK a few weeks ago in Ethereum San Francisco. And during that event, there are 5 teams actually building their own applications on top of Celer's SDK. We found a lot of interesting ideas. For example, some teams are building something like the option prediction market. Someone are doing something like financial derivative of gas fees. Okay, so that's basically the current progress of Celer Network. So now let's move on to the technology stack. So the first question that I want to ask is, what is the current stage of blockchain? I think it's still in this age. It's basically currently the blockchain is still in the Nokia age. So it's slow, it's very dumb. Okay. And we currently see that slows value transfers on the current blockchains. Basically, the Ethereum of Bitcoin can only support around 10,000 transactions per second. Okay. So pretty much everyone agrees that we need scalability right now. Okay. But I think another important question that we need to answer here is, what is the end goal for blockchain scalability? Because someone say, oh, I can improve my blockchain scalability to 1,000. Someone say I can achieve 10,000 tickets. Some other guys may say I can achieve 1 million tickets. So what exactly is the end goal for the blockchain scalability? And our vision is that the scalability of the blockchain should match the scale of internet. So internet, which is also called Web 2.0, what internet enables is the global efficient transfer of information bits. Okay? So in 1 second, there are like 2 million emails exchanged on the internet. There are like 65,000 Google searches, and there are also like 53 terabytes data being transferred on the internet every second. Okay. And blockchain as Web 3.0, what it should enable is a global efficient transfer of value instead of just information bits. Okay? So if we assume that every 1,000 kilobytes information transfer contains one value transfer, then the kind of like a scale we need for the blockchain is around 500 million. Okay? So that's a kind of scale we need for the blockchain in order to match the internet scale. But it's not 1,000, it's not 10,000, it's not even 1 million, it's 500 million. So how could ever achieve this kind of goal? Okay, someone may just say we can continuously to improve the performance of their current blockchain system, okay, by using something like a new consensus algorithm or using some like new techniques like sharding. Okay, but there's actually a fundamental bottleneck for any blockchain system. Okay, so no matter how hard you try to improve the blockchain system performance, it has an upper limit. So where does this upper limit come from? So because as long as every node in the blockchain system needs to agree on every single transactions, then the performance of this system will be no better than a system where a single node dictates everything. Okay? So any distributed system, its performance will be bottlenecked by the processing speed of a single node. Even with sharding, as long as there's some cross-shard transactions, with more and more nodes joining the network, then the speed up caused by sharding will diminish. Okay? So our goal is is right above. Okay, so like 500 million. So there's still a huge gap between where we are and what we want. Okay, so how can we compensate this kind of gap? And our vision is that layer 2 scaling is a kind of the inflection point to bring the blockchain to mass adoption and to match the internet scale. Okay? So here I just want to give you a very quick background introduction about the layer 2 scaling. So the basic idea of blockchain scaling is to bring most of the on-chain transactions or state transitions from on-chain to the on-chain. Okay? While only resulting to the blockchain when you need to settle the state or when you need to dispute over the state. So because we believe that the core value of blockchain should be the generation of trust instead of handling every detailed computation step and every detailed state transitions. Okay? So in this way, the blockchain is like a super report. We only use blockchain when necessary, when there's something that we really want to dispute, we really want to settle. Okay? So in this way, the layer 2 like scaling solutions achieve a fully scaled out system. So basically, because most of the cases, you do not require others to interrupt or to see your transactions. So most of the nodes can conduct their transactions in parallel. Okay, so as more and more nodes join the network, the throughput of your blockchain system will also increase linearly. So these are kind of like a fully scaled out system. Okay? And also, since we have the blockchain as the underlying super record, so basically the layer 2 scaling is as secure as the underlying blockchain. Okay? And currently there are multiple layer 2 like scaling solutions like state channel and sidechain and also plasma and also something like a TrueBit. Okay. So what Celer network is currently focusing on is the state channel. So I will give you some introduction about state channel in this presentation. So this is a very simple example about an option payment channel. Okay. So let's say Alice and Bob and want to send some payments option. So what are they going to do? So the first step is that both parties will deposit some amount of money into some on-chain smart contract. Okay? And then after they deposit money, so basically we see that there's a payment channel established between Alice and Bob. then they can start to send option transactions, as many option transactions as possible. The only thing that we require them to do is to sign the state proof or the balance proof after they send each payment. So basically, this balance proof will show, okay, how many balance Alice has and how many balance Bob has, okay? And in the case that Alice wants to withdraw his money, he wants to cash out. So then Alice will submit the signed balance proof to the on-chain smart contract, and Bob say, I agree. This is indeed the latest balance proof that we have signed. Then the smart contract will basically distribute the balance according to the submitted balance proof. But in the case that Alice is a bad guy, he wants to steal some money from Bob, he might just submit some old balance proof. Okay, so this old balance proof is still valid. It's still because it still contains the signature of both parties, but it's just an old balance proof. Okay, so in this case, Bob will say, okay, I disagree. I have a newer and latest balance proof. Okay, so here the Bob's state proof balance proof is number 49. And Alice's balance proof is number 47. So the smart contract will only take Bob's balance proof because it's the latest and distribute the balance accordingly. So in this way, the security of the transactions in the blockchain will be fully guaranteed by the blockchain layer. Okay, so previously we have been talking about just establishing a payment channel between immediate, direct payment channel between the two parties. But know that the previous process still involves some on-chain transactions. For example, the first step is for you to deposit some money onto some on-chain smart contract. So if you want to pay everyone in this room some money, you basically you need to open a channel with everyone. So that's all like an on-chain transaction, which could be very slow. Okay. So another idea is that although I do not have a direct channel between Alice and Bob, but we can find some intermediate guy to help you to relay the payments. Okay. So in this way, we have a notion of a state channel or payment channel network. So basically, when Alice wants to send Bob some money, he can first send some payment to David, and David can further relay this payment to Bob. But of course, in order to guarantee that the intermediate guy, David, do not steal the money from Alice, we need some more mechanisms, which is called hash time lock. For the sake of time, I will not mention the details about these techniques because it's pretty standard in state channel. Okay. And the Celer network is the first coherent off-chain scaling architecture. So basically, it contains two components. The first component is called C-Stack, which is basically the Celer network's technology stack. The second component is the C-economy, which is Celer network's crypto economy design. Okay. So in today's presentation, I will put most of the time on the technology stack. Okay. So on our technology stack, we basically have a layered architecture. We have 3 layers: the C-channel layer, C-route layer, and C-less layer. I will mention each layer one by one. Okay, so the lowest layer, C-channel layer. So this layer is about how can we construct a state channel. So this is like the link layer in the traditional computer network. Okay. And there are 2 key features enabled by Celer network's C-channel layer. The first is the general state channel. The previously, I just mentioned an example about how you can set up a payment channel between 2 guys. But what if I want to support something more than payment? What if it's a generalized state transitions? Okay? So basically, in Celer's C-channel layer, we enable generalized state channel. So basically, that allows an off-chain execution of a smart contract. Okay? And the second important feature provided by C-channel is called conditional payments. So conditional payments is just like, it's not simply I send you some money, it's I send you some money conditioned on the fact that some condition has been satisfied. For example, A pays me $5 if some condition is satisfied. So here the condition could be dependent on any on-chain verified state. So what I mean by on-chain verified state, it could be any state that has already been put on the blockchain, or it could be any state in the generalized state channel. Okay, so I will give you a simple example about the use case of the two features provided by the C-channel layer. So let's say Alice and Bob wants to play a chess game, and they bet $5 in this game. Whoever wins, the loser will pay the winner $5. So if we want to realize this kind of logic on the blockchain, it's very simple. We just write a chess game smart contract, and each of them put $5 into the smart contract. And then they start to play the chess. But note that since this is an on-chain transaction, every move they make is actually very, very slow. Okay? So we just let them to play for a while. Okay? So it's a very, very slow process if it is play on-chain. Okay? And after 1,000 years, all the guys have become old, and this game has finally ended. Okay? And let's say I finally win. Okay? And the smart contract will give the money. Okay, that's totally unacceptable, right? So with C-channel, things have become very, very different. So if you're using C-channel, like the two key features to realize the previous scenario, the first thing they will do is both parties will send each other a conditional payment, saying that I will pay you $5 if you win the game. Okay, and then they can start to play the game. Okay. So the game itself is a general state channel, okay? And the only requirement for both parties is that after each move, both parties need to agree on this is a legit move, and they need to sign the board state, okay? And the entire chess playing process does not involve any on-chain transactions. And this is also called the pure off-chain contract. So that basically allows the off-chain execution of the smart contract. And after the game has ended, Bob Alice say I win. And since we have previously sent a conditional payment from Bob to Alice, this conditional payment will become an unconditional payment because we have known that Alice indeed wins the game because both parties have signed the board state. Okay. And here's a formal specification. If you want to construct a general state channel, for example, you need to define what is the participant of this general state channel, what is the initial state, and what is the latest state proof for this general state channel. And for the sake of time, I will not mention the details about these constructions. If you're interested, feel free to check out our white paper. And there are also other out-of-box features provided by the C-channel layer, such that we have a native support for multi-hop transfer. And we also support something like the off-chain address translator, value settling, and so forth. Okay, now we are done with the first layer, the C-channel layer. So C-channel layer basically tells you how to construct a state channel between the two parties, okay, or multiple parties. In this way, we can basically construct a network with multiple state channels, multiple nodes. So the next question is that, as I mentioned earlier, we can actually enable a multi-hop transfer or multi-hop payment in a state channel network. Okay, so one critical question here is that how can we route payment in a network that consists of payment channel? Okay, that's actually a very challenging problem and still an open research problem. And for example, Lightning Network and radio networks, they spend a lot of time trying to solve this problem. Okay. But why is the payment routing is very, very difficult in an off-chain state channel network? That's because the link model is fundamentally different. Okay? So in the traditional data network, in the computer network, so if you have a link between the two nodes, and this link has a bandwidth of 100 megabytes, then its bandwidth always remain 100 megabytes forever. So this network environment is relatively stable. But for payment state channel network, it's very different. So because in a state channel network, the link between the two parties is basically the state channel or the payment channel between the two parties. And the bandwidth of this link is basically the remaining balance for both parties. So as long as I send you some payments, the remaining balance, all the bandwidth of this link will dynamically change. So this is a highly dynamic network. Okay? And existing payment routing algorithms are all variants of distributed shortest path routing, like the flare routing algorithm using Lightning Network, and also some research work like speed murmurs. So this kind of distributed shortest path routing is not suitable for a highly dynamic network, because whenever the network topology changes, so basically this distributed shortest path routing always needs a lot of time to reconverge. So in Celer network, we proposed a new payment routing algorithm called Celer. So Celer uses a very different design philosophy from the traditional shortest path routing. So its design is based on two principles. The first principle is to follow the congestion gradients. So basically, I want to route my payments in the direction that will reduce the network congestion into the maximum extent. Okay? So it's just like, think of like a water flowing from the top of a hill down to the foot of the hill. You do not have to tell the water, okay, this is a path you should follow. All the water needs to follow is the gravity. So here the gravity is like the congestion gradient. And the second principle is to keep the payment channel balanced. Basically, we want to avoid the situations where some guy just keeps sending the payment to the other guy and without receiving any payment. So in this case, one of the parties in a payment channel will quickly run out of their balance and no longer be able to relay any payment. So we want the long-term sending rate of each node equals the long-term receiving rate of that node. Okay. So basically, if I found, okay, I have sent too much money to you, then basically I will probably do not choose you to relay my payments until you send back some tokens. Okay, and we also have some simulation results in terms of the performance of our Celer algorithm. So basically, it improves the current state of the ARM routing algorithm, payment routing algorithm by 20 times. And one thing I want to mention is that the performance of our Celer algorithm is actually mathematically proven. It is probably optimal in the sense that as long as there exists some routing algorithm that can support the given payment request, then our algorithm can also do so. Okay, so it's mathematically proven. Okay, now we are done with the second layer. The upper layer, COS, is has the flavor of an operating system. Okay, so why do we need this layer? Because according to my previous introduction, we can see that in order for the developers to build an application that uses the layer 2 scaling is actually very difficult. Because the developer needs to maintain the state management. They need to know how to store the state, how to sign the state, and also they need to control the communication protocols. Okay, that's actually very, very tedious and also very hard implementation details. So in this way, we want to build something like an operating system. So it's like a blockchain is just like computer hardware, and the Celer is just like Windows and Linux, which abstract all the kind of low-level details from the developers. The COS layer will handle the communication protocol, the state management for the developers, and provide developers with easy-to-use development frameworks, and so that they can just like easily plug in Celer's layer 2 scaling solutions into their own decentralized applications. Okay. I will not mention the details about this layer. Okay, so now we have done with the Celer Network's technology stack. I will quickly go through the Celer Network's crypto economics design. So this part is also very, very important because this part is used to handle some of the challenges or the trade-offs that we have in option scaling ecosystem. Okay, so basically we have three economic mechanism designs which are used to solve different challenges in the option scaling systems. So the first challenge is called the state availability challenges. Okay. So the state availability challenges is like this because the state channel basically requires both parties to always remain online because otherwise if this guy, the Bob, becomes offline, then the Alice basically, suppose she's a malicious guy, she can submit some old proof. But in this case, the Bob has already been offline, he cannot respond. Okay? So, and after some timeout, the on-chain smart contract will just like say, okay, this is indeed the latest state proof I say because Bob does not respond. Because Bob actually cannot respond. Okay? So in this case, the Alice will successfully steal some money from Bob. And that's a kind of like a security concern if one party actually goes offline. So in order to solve this state availability problem, Celer network proposed the notion of state guarding network. So state guarding network is actually a special sidechain, which consists of a set of state guardians. So in order to become state guardian, you need two qualifications. One is that you need to build up or run a reliable and always online software service for the end user. The other requirement is that you need to stake some Celer tokens onto some blockchain. Before a certain user goes offline, he needs to first submit his stake proof to the state guarding network and saying that please help me to guard my state for 1 hour and I'm willing to pay $1. Okay. And then, of course, there will be some other guys who also want to guard their state when they become offline. And for each of these kind of state guarding requests, we will select a set of state guardians for each of the requests. Okay. And one thing I want to mention here is that the more Celer tokens they stake, the more state guarding requests they will get assigned. Okay. So here, guardian number 2 will get the most state guarding requests. And each of these state guarding requests comes with some service fee. So here, more Celer tokens staked, that means you have more work to do. So Celer token is like the right to work, okay? And it also means more money. Okay. And the details regarding the process is like this. After the user becomes offline, he submits a state proof to the state guarding network. And we have selected a set of state guarding for this request. And each of this state guarding is allocated a dispute slot. Okay. So if some malicious party submits some old state proof, then each of the state guarding will, like one by one in turn, submit the state proof for the offline user. But in the case that some state guardian is also malicious, he must collude with this kind of malicious user. So in this case, the next state guardian will say, okay, the previous state guardian did not do his job. So I will just slash his Celer token and give it to the state guardian that actually does his job. Okay. But in the case, and this state guardian will be just kicked out of their state guardian network. So this is a way we achieve trust-free monitoring. And in the case that all of these state guardians are actually malicious, then the user will find, okay, actually all of you do not fulfill your job. So when I come back, I will submit a proof of malicious behavior to the blockchain, and the blockchain will slash the Celer token for all of them and give it to the end users. That's a compensation. Yeah. So basically, the state guarding is a complex section that enables the trust-free state availability service for the end users. Okay. And the second challenge is called the network liquidity challenge. Because in the future, we envision that the payment channel network is look like this. There are lots of several big circles. So these big circles represents the option service provider. Okay? And there are lots of end users, which are small circles, will connect to each of the option service providers. But one trade-off that the state channel technology make is that is the liquidity, because basically they need to lock up their liquidity into the network before they can make transactions. Okay? So that's called scalability versus liquidity trade-off. And in order for the service provider to connect to many users, the service provider needs enough liquidity to open a channel with a lot of users, right? But where does this liquidity come from? Okay. because some guys may have the technology to build a reliable auction service providing infrastructure, but they do not have enough money. But some other guys, they may have a lot of tokens, but they do not have the technical capability to build such a service. So there's a mismatch, and will slow the adoption of the layer 2 scaling solutions. So what we propose is called the network is two economic mechanisms. One is called the proof of liquidity commitment mining. The other is called liquidity banking auction. So the proof of liquidity commitment is basically to encourage users, to incentivize users to lock up their liquidity in the system. So according to in a reward for some Celer token. So basically it's like a virtual mining process, and the mining power equals to the amount of liquidity they want to lock up times the kind of duration they want to lock up their liquidity. Okay. And the second step is called the liquidity banking auction. So basically it's like a crowd lending process which helps some guy to lend some liquidity from the other crypto whales. So let's say this guy say, I want 100 Ether for 30 days with a maximum interest rate of 1%. Then those guys who have enough, like ETH will submit their bids, which corresponds to the interest rates they want to charge, and also the amount of Celer token they want to stake. So Celer token here is like the priority token. Okay, and basically, we will calculate a score for each of the bids, and the one with the highest score will win. And we use the second score auction here. So basically, the winner will take the bid of the second highest bidder. Okay. So that's basically the crypto economics design of Celer networks. And one important remark I want to mention here is that the crypto economics design of Celer network actually completes the cycle of the auction ecosystem. So the previous C stack, which is the technology stack, is all about how can we efficiently move state from on-chain to off-chain. And here, this kind of crypto economics design is help us to answer the question that how can we securely move the state from off-chain to on-chain. So in this way, we actually complete a cycle for the off-chain ecosystem. Okay. Then that's basically today's presentation, and feel free to join our Telegram or WeChat group, and also feel free to try out our app. And okay, and the final things I want to mention is that we have seen a lot of layer 2 scaling solutions, as I mentioned, state channel, plasma, and sidechain. And we see the tendency to combine all these layer 2 scaling solutions into one unified framework. Because each of these solutions actually achieve one trade-off point in terms of state availability, privacy, and finality time. So in next year, we will publish our thoughts about the unified framework for all the layer 2 solutions, and it's called Celer Network 2.0. Yeah. So that's basically my presentation today. Thank you very much.